Okay, last differential equation that I'm going to record a video for. There are two more on the handout there. Hopefully, after I've done these four, you should be able to work through those other two. But if there are any questions about them, just shoot me a text. Let me know. I'll be happy to help with those. But I'm just going to record videos for these four. This one, similar to the third one that we did, is another context problem. So at the beginning of 2010, a landfill contained 1,400 tons of solid waste. The increasing function, typically if they include vocabulary like that, it typically means we're going to use it sometime. The increasing function W models the total amount of solid waste stored in the landfill. And it kind of makes sense that that function is increasing. Landfills, you're always adding waste. That number typically doesn't decrease. It's the purpose of a landfill. Planners estimate that W will satisfy the differential equation dW over dt is equal to 1 over 25 W minus 300. Look familiar? That's very similar to the differential equation from problem number 3. The following year, we're going backwards here. This was 2011. The previous one was 2012. So anyways, for the next 20 years, okay, so we've kind of got a restriction on our domain there. W is measured in tons, T is measured in years from the start of 2010. Part A, use the line tangent to the graph of W at T equals 0 to approximate the amount of solid waste that the landfill contains at the end of the first 3 months of 2010. And look how nice they are. They even remind you that T equals 1/4. You don't use 3 because time is in years. So 3 months is 1/4 of a year. So they want us to use the line tangent to the graph. The line tangent to the graph at T equals 0. So what's our initial condition at T equals 0? How much is in there? 1,400. Okay, so let's use our tangent line. That means we need our slope. That comes from our differential equation. So dW over dt is equal to 1 over 25 times the weight. The initial condition there is 1,400 minus the 300. So that's 1 over 25 times 1,100. Yeah. Okay, well, let's just think about this for a second. 25 goes into 1,000 40 times, right? If you're having trouble with that, anytime 25 is involved, I think about quarters, okay? So if I'm talking about $1, there are 4 quarters in $1. So, or in 100, okay? If we're talking about cents. So I've got 1,000, so I need to multiply that by 10. So I got 40, and then I got another 100, so that's equal to 44. Just a little side note on that. Okay, so that's our slope. So we've got y minus 1,400 is equal to 44 times x, because it's x minus 0. So let's see here. For the first 3 months at time t equals 1/4. So y minus 1,400 equals 44 times 1/4. Look how convenient that is. Those numbers work out because this is calculator inactive. So 44 times 1/4 is 11, and we're adding 1,400 to that. So that would be what? 1,411. You get tons. Always put units. Anytime there's context, put units. I didn't really do that. I don't know if I did that on the bird problem. I don't know that I really need to do that with the bird problem. But anyways, put units if you can. You get 1 point for the derivative at time 0, and you get 1 point for your answer. Part 2. Find the second derivative in terms of W. Again, this is exactly what we had to do in the last problem. Find the second derivative in terms of W. So let's do that, and then we'll look at the rest of the problem. So d squared W over dt squared. The constant stays in front. Derivative of w is dw over dt. The derivative of 300 is 0. Okay, but remember they want it in terms of w, so we've got to go back in there and plug in that original differential equation that they gave us. So we've got, let's see here, 25 squared is 625. So we get 1 point for that. Let's look at the rest of the question. The rest of the question says, use the second derivative to determine whether your answer in part A is an underestimate or an overestimate of the amount of solid waste in the land that the landfill contains at time t equals 1/4. So let's find out what that value is. So let's see here. 1,411 was our estimate. So this second part is going to be positive. So we've got positive times positive. So since you really didn't have to show that, but you can just state it. Since d squared w over dt squared is positive at t equals 1/4, the answer to part A is, well, let's think about this. If the second derivative is positive, that means our function is concave up. Any concave up curve where the, well, and this one's increasing. They told us it was increasing. So if we're increasing and we are concave up, our tangent lines are under the curve. So this is going to be an underestimation. Is an underestimation. Okay. So 1 point answer with reason. Easy enough, right? All right, part C. Find the particular solution to the differential equation with the initial condition. So let's do that. dw over dt, I always copy it down. Although on the actual exam, they're going to have these questions, these parts broken up. So really, I mean, this line is going to be right above where you start your work for part C. So it's already there. So if you just want to jump into your separation of variables, you can kind of do that. You don't have to recopy the problem because it's going to be right there. Again, same as always, we're going to end up dividing. Very rarely does separation of variables not require dividing something. So again, 1 point for separation of variables. Let's anti-differentiate. This will be the natural log of w minus 200. This value is always going to be positive. We really don't need the absolute value bars because the weight of the landfill, it started at 1,400 and it's increasing. So this is always going to be positive. But anyways, the other side is going to give us 1 over 25t plus c. This time, we still only get 1 point for our antiderivatives, 1 point for our constant of integration. Let's use that constant of integration. Oh, back to the, I forgot. We don't put a negative in front of this one because the variable was positive, okay? So this is just positive right here. So w is 1,400 in our initial condition, and that's times 0. So that is going to give us our C. The natural log of what, 1,200 is equal to our C. 1,100. Where did 200? Oh, I wrote down 200 instead of 300. Once again, what did I tell y'all about like checking what you write down before you go to town on your problem? See, that would have cost me a point. That would not have been good. Let me fix this. And again, it's a reason why it's good to not to have to recopy it. I was so busy explaining about not recopying it that I didn't even copy it right. Okay, 1 point for using your initial condition. So let's go back, plug that number in. Okay, that's not supposed to be 11,000. That's supposed to be 1,100. Okay, solving for W. Nothing in front of our natural log this time, so we can jump right to our E. I'm not going to show it this time. Y'all know what happens here. That cancels, so we've got 1,100 E to the, and I'm going to write in shorthand just T over 25. 1 over 25T is the same as T over 25. And then move that 300 over. So 1,100 E to the T over 25 plus 300 equals our W. Remember, come over to the side, plug in that initial condition. That's E to the 0 plus 300. Does that equal 1,400? Well, yeah, 1,100 plus 300 is 1,400. So we're good. Okay, 1 point for solving for W.